Welcome to a lesson on Venn diagrams and set operations. The goals of the video are to define a Venn diagram, use Venn diagrams to show relationships among sets, and also to define set operations. A Venn diagram is a visual diagram that shows a relationship of sets with one another. The set of all elements being considered is called the universal set and is represented by a rectangle as we see here. The complement of A is the set of all elements in U, not in A. Or using set builder notation, the complement of A is the set of elements X such that X is an element of U and X is not an element of A. So if we let the universal set be the integers 1, 2, 3, 4, and 5, and A was the set containing elements 1, 2, and 3, then the complement of A would be the elements in U that are not in A, so it would contain the elements 4 and 5. So the elements 1, 2, and 3 would be inside set A, and the elements 4 and 5 would be outside circle A. Set A and B are disjoint if they do not share any common elements. So using a Venn diagram, set A and set B would not overlap. So here if the universal set was a set containing 1, 2, 3, 4, 5, 6, and set A contained the elements 1, 2, 3, set B would not be able to contain 1, 2, or 3, but it would have to contain elements within the universal set. So maybe B would contain 4 and 5. So for the Venn diagram, 1, 2, and 3 would be inside set A, 4 and 5 would be inside set B, and 6 would be outside both circles. In this diagram, B is a proper subset of A. This means that B is a subset of A, but B does not equal A. Using the symbols discussed in the previous video, we could say that B is a subset of A and B does not equal A, therefore B is a proper set of A. And instead of using this symbol for a proper subset, sometimes you'll see this symbol here used. So if we let the universal set contain the elements 1, 2, 3, 4, 5, 6, and let's say set A contains 1, 2, 3, and 4, set B would have to contain some of the elements in set A, but not all of them because they're not equal. So maybe set B would contain 1 and 2. So we'd have the elements 1 and 2 inside B that are also inside set A. 3 and 4 would be outside set B but inside set A. And then 5 and 6 would still be in the universal set. And if we have equal subsets, that means B is a subset of A and B is also equal to A. So all the elements in A and B are in the same circle. So if the universal set was 1, 2, 3, 4, 5, if set A contains 1, 2, and 3, then in this case B also contains the elements 1, 2, and 3. So we'd have 1, 2, and 3 here, and then outside A and B would be 4, 5, and 6. So if A is equal to B, we can say that A is a subset of B and B is also a subset of A. The intersection of A and B is a set of elements in both set A and set B. Using symbols, we have A intersection B is equal to all the elements X such that X is contained within A and contained within B. So the universal set is equal to 1, 2, 3, 4, 5, 6, and we have set A equal to 2, 3, and 4, and set B equal to 3, 4, 5. We can see that sets A share the elements of 3 and 4, so that would be in this region here. So 3 and 4 would be in this region here. And set A also contains the element 2, so there would be a 2 here. And then set B also contains the element 5, so we'd have a 5 out here. And that leaves the elements 1 and 6 in the universal set. So the intersection of A and B contain the elements 3 and 4. And now let's talk about the union of sets. The union of A and B is the set of all elements in set A or set B. So A union B is equal to all the elements X such that X is contained within A or X is contained within B. So the big difference between intersection and union is intersection we have an and, union we have an or. Using the same sets as we did for the intersection example, it would look the same, except now the union would be all of the elements that are in A or B. So we'd be talking about this entire region here, because an element only has to be in one of them in order to be in the union. So A union B in this case would be all the elements in the universal set except 1 and 6. So we'd have 2, 3, 4, and 5. And a couple things to mention about the empty set. Any set A intersected with the empty set will equal the empty set. And the union of any set A and the empty set will always be the set A. I think we'll stop here for part 1 and take a look at some additional examples in part 2.